2-7 Strategies for Evaluating Limits. The first technique you should use is substitution. See if it works. If you put those numbers in, you get the answer. And that way you're using the limit theorems and you get your limit. There is a caution though. A situation like this where you substitute 6 into here may not be such a good idea. You're going to get the answer 0, but this isn't a good idea because if you substitute 6 in, 6 is not part of the domain. In this situation right here, we're approaching 6 from the right-hand side when actually the domain is only values from the left-hand side. So we can't evaluate this. Here's another expression that looks really pretty difficult, but you put 3 into all of these and you do get an answer. So always try substitution. In this case, when we try substitution, we get an indeterminate form, which means we might be able to get an answer or we may not. And factoring is something that you ought to try. So in this case, we factor. We found there's common factors. This creates the hole in the graph. If we reduce, we get an expression that has the same limit as the original, and we can substitute. Here's another example of, again, if you substitute in, you're going to get an indeterminate form. This is always what you should check first. We go ahead and reduce, and this expression has the same limit as this one. And if we substitute 2 in, we're going to get 0 over 3, and we know that that limit will be 0. Okay, again, trying to substitute, we get a 0 over 0, and we're going to do some algebra, get a common denominator. Rewrite this complex fraction like this. We want to actually take this and we want to write it as negative x minus 2. And so we've put the negative here with a negative 2. And we can reduce. We have an expression that has the same limit as the original. We can substitute and find it. Okay, here's another situation. Again, if you put 3 in here, you're going to get an indeterminate form. Right here, there's no factoring. What we do instead is we multiply by the conjugate. So here is the number 1 that we're going to multiply by. The numerator becomes this, and this is actually equal to this factor. So when we do our reducing, we're going to get, again, a limit here that has a limit expression that has the same limit as this expression. We can substitute and get an answer. All right, go ahead and try that. Stop the screencast and see if you can do these on your own. Here are the answers. I multiplied by the conjugate, did some simplifying, and then evaluated. Factoring and canceling. Be careful when you have an absolute value. With an absolute value, remember you have to guarantee that your outcome is positive. Since these values right here are smaller than 7, we know that in here we're going to have a negative expression. So multiply by a negative 1 to ensure that this outcome is going to be positive, which will allow us to now reduce, have an expression that has the same limit as the original, and substitute. Another plan is to combine these terms first, simplify them, and then take the limit. Again, stop the screencast, see if you can do this, and I will give you the answer. And here's the answer. I went ahead and I just combined, multiplied everything out, and I noticed that my 5x squared and my 5x here canceled. I got this. There were some h's that I could reduce, an h here and one of the h's here. So I got this expression. As h goes to 0, it'll make this go to 0, and my answer is 10x. Over here, it's working with fractions. Get a common denominator. The 3's are going to go to 0. I'll have a negative x, and I can do some reducing here, and then evaluate. Okay, a special case involving the sine function. When we involve the sine function like this, our limit becomes 1. Let's look at it graphically. Right here I have the function, and make sure you're in radian mode. And I went ahead and graphed it. And right now what I'm going to do is press the trace button and let's see what happens as we get closer to 0. When we get close to 0, on 0 we have no y value, and if we go past that we do start getting some values. So there's a hole in the graph right here, and by looking at the graph it looks like the answer is 1. Let me go ahead and take a few minutes to prove that to you. So we want to go through a proof, and what we're going to do is we're going to look at it by squeezing an expression between two other expressions that we know the limit of. So right here we have 3 areas that we're going to find. The first area is the area of this triangle right here, and this is a unit circle. So the area of the triangle will be equal to 1/2 the base, and the base right here is from a unit circle, so it's 1. And this is an angle of x, and so the height right here will be sine of x. So here's the value of the area of the triangle. Now the area of a sector, back in geometry, the area of a sector was m/360 times pi r squared. But we're in calculus, so we don't work with degrees, we work with radians. And when we do that, the pi's are going to cancel. We're going to get a 1/2, and this m really stands for the number of the angle. And remember, this isn't degrees now, it's actually x. And our radius in this case is 1, so 1 squared, and that's how we get this value. Now we would like to figure out the area of the big triangle right here. Now this slope of this line is the tangent of x, and I know that because this is x, and this is the sine of x, and this is the cosine x, and it's passing through the origin right here. So if x is equal to 1, then I know that the height here must be the height of the slope, which is tangent of x. So the area of the triangle is going to be 1/2 the base, which is 1, and the height will be the slope of that line, which is the tangent of x. And that's how we get this. So let's go ahead and multiply through by 2. And when we multiply through by 2 in this inequality expression, I'm going to get this expression right here. Let's see. It says multiply by 2 divided by sine of x. So as soon as we get these two 2's reduced, then we're going to do the reciprocal here, or divide by sine. And so we're going to get a 1 here, divide by sine here, divide by sine here. Now that is sine of x all over cosine of x divided by sine of x, and we're going to get a simplified to 1 over cosine of x. We're going to take the reciprocals, and when we do that, the inequality must change. So we're going to get this expression right here. So we're getting cosine of x, sine of x over x, and 1. Remember that the sine of x over x looks like this. We know 1 is a constant function, and we have the cosine of x. Let's take a look at this picture. So sine of x is the one in between. You can see it's the black curve. 1 is a constant, it's the green, and then cosine of x is the red. So this is sandwiched between these two. So I want to find the limit as x approaches 0 of cosine of x, and then I'm going to find the limit as x approaches 0 of sine of x over x, and then I'm going to take the limit as x approaches 0 of 1. Well, I know this answer is 1, and I know as x gets closer, this is 1. So this unknown limit is sandwiched between two limits that I know, so it has no other choice but to be 1 as well. All right, so what we've just proved is as x gets closer to 0, the sine of x over x is equal to 1. And the reciprocal is also true. And we can go through a squeeze theorem again, and we're going to find that this is equal to 0. You need to graph this to take a look at it and convince yourself it's equal to 0. Now here's how we go about doing some problems. You can see the limit as x approaches 0, sine of 3x over x. The arguments must be the same, and the arguments are not the same right now, so I'm going to multiply the top and bottom by 3, and now the arguments are the same, so it looks just like this. So this whole thing is going to 1, and 3 times 1 is 3. Now this looks like this one up here, except this has the argument 7. So I'm going to multiply top and bottom by 7. 7's going to come out, and now I have this argument matching just like it's up here. So I know this whole thing goes to 0, and 7 times 0 is 0. Now with tangent of 2x over x, I'm going to change the tangent to sine over cosine. So I have this sine over cosine like this. And I'm going to, I know that this argument and this argument have to be the same, so I'll multiply the top and bottom by 2. And when I get the top and bottom by 2, I'm going to have this argument now, 2x and 2x, so this whole thing goes to 1. And when I substitute in here, I know that this cosine, this is going to be cosine of 0, which is 1, and then the answer will be equal to 2. Okay, multiplying numerator and denominator by the reciprocal of the highest power. In this case, I am getting infinity over infinity. And when you have infinity over infinity, what we can do is we can divide by the highest power of x appearing in the denominator, so that we can get some control over the denominator. And when we do that, we get all of this. And as x approaches infinity, we know as x goes to infinity, this denominator gets very large, and so the fraction goes to 0. So all these go to 0, and the answer is 5/6. All right. Now, when the denominator is getting smaller and smaller, when it's going towards 0, then the whole fraction is getting larger and larger. So as x gets closer to 2 from the right-hand side, this is a small positive number. Now up here, as we get closer to 2, this is a negative number, and negative and positive make negative. But since you're dividing by a very small number, the whole absolute value is getting very large, and so there's the answer. Okay, here's a summary of some of the things that you need to know. When you have a and b as the exponents, and if a is less than b, then a isn't growing as fast as the denominator. And so if the denominator is growing faster, then the whole fraction is really getting smaller and smaller and going to 0. Now, if these two happen to be the same, then we call this the principle of dominance. You can go through that process I showed you about dividing by the highest power, or you can remember from your pre-calc that it's just the coefficients of the highest power. When the denominator is, or when the numerator exponent is larger, then the numerator is getting larger faster than the denominator, and therefore it's going to be infinity or negative infinity. Okay, take a look at these problems. Stop the screencast, see if you can do them, and I will show you the answers. And here are the answers. This is the end of the screencast.